So Boyle's law is between pressure and volume, and how are they related? Now, inversely proportional, right? Also it's indirectly, same thing.
Hi, is Tucker absent today? Thank you.
Now, in the book, one book says that Boyle's law is PV equals K. Your book actually says P1 equals P1 V1. What's that all about? And remember, if two things are inversely proportional, they're on the same side equal sign, right? If this goes up, this goes down, right? And proportionally. And if I took the P and the V reading and multiplied them, I'd get the same number, whether it was P1, V1, P2, any place on this graph. If I take the X and Y value and multiply them, I get a constant. And that's why PV equals a constant. I know you want that to be exact because in math class they want to be exact. This with error, these are exact. When you're talking about something's 50,000 and this is 49,950, you said, that's not the same. Yeah, it's the same. It's the same. So it's constant. Got that? All right, that was Boyle's law. And then we had another one. This was not in your book. What was this one all about? Why would they did this with gases? That's why I brought this up in this chapter, because the first time they ever tried to figure this out, I think it's kind of weird. They were thinking, hey, the volume gets smaller, the temperature gets colder, the volume gets smaller, and so temperature goes down, volume goes down. Temperature goes up, volume goes up. How's that related? What's the relationship there? Inverse or direct? Here, this is direct. You go up, I go up. You go down, I go down. There's inverse. See that? So what was the relationship between temperature and volume? Direct. Now, this, though, is not a direct proportionality because it doesn't go through 0, 0. But you also have a scale that has positive and negative numbers. If I were to change those numbers to Kelvin, that's what Charles' law is. The volume of a gas is directly proportional to the Kelvin temperature. So if you were to make the Kelvin temperature get 5 times greater, what would happen to the volume? It'd get 5 times greater. If you cut the Kelvin temperature in half, the volume of the gas is going to be shrunk into half. All right, so that's a quick things here. Now I want to show you, let's talk about this right here. This is actually a lot about last chapter. So this should make sense to you. How does a hot air balloon work? Let's think about that. Well, first of all, which one is more dense? This kind of air or hot air? Which one's more dense? Or which one's less dense? Hot air is less dense. When you heat that air, it starts spreading out. Just like you take a balloon out of the freezer and let it sit in the room, and you'll see it start to expand. As it gets warmer, the volume gets higher, doesn't it? Okay, so we're going to have a big envelope, a very big balloon part. It has to be pretty large. And so right now, you turn on the burners and you put this hot air in this bag. Now, this is a lot less dense than this air here. So what's going to happen when this hot air displaces the other air? What's going to happen? What's Archimedes' principle? What's going to happen to the balloon when you put hot air in it? And it gets really big. The balloon's really big now. And it's got hot air in it. What is it doing? Is it displacing anything? Okay, so Archimedes says the buoyant force is equal to the weight of the displaced fluid. And I know the air doesn't weigh very much, so you better have a pretty big balloon if you're trying to get some buoyant force, and they do. So when the balloon's sitting on the ground, maybe buoyant force equals weight. And then they turn on the burners again, and the balloon gets a little bit bigger. And then when buoyant force is greater than weight, then what does the balloon do? It rises, doesn't it? Accelerates up. And then when you get up, if you don't turn the burners on, it'll start rising up. But if you don't turn the burners on, then what happens to warm air when you don't keep warming it? It cools. And so your balloon goes, it expands, and then it cools. And so you turn the burners on again. But a good balloonist can actually keep you at the same altitude. They're good enough to say, I don't want to go up or down. I want to be neutrally buoyant at 100 feet up. And I've seen them in Africa. They go where the elephants are, and they, you're only sometimes only 60 feet up in the air. They don't have to worry about power lines. The trees aren't that big there. So maybe they're like 60 or 50 feet off the ground. They just go the whole way, wherever the wind takes them. They can't really control where they're going. All right. Have you ever seen some movies with balloons and they have the big heavy sandbags on there? Oh, that's good. But so if for some reason something happened, you started to fall, maybe started to descend faster than they wanted to, they might drop some sandbags. What would that do? That would make your weight be less. And so maybe if you're going down too fast, they drop some sandbags and they start going up a little bit. Yes.
So with blimps, doesn't
I'm doing blimps next, but go ahead. It's different.
don't the like the cabin and everything, it has to be like super lightweight, right?
Yeah, but the blimp's pretty big. And matter of fact, the blimp's a lot bigger than a balloon, and you can carry a lot more people in the gondola.
So weren't there like war blimps in World War I?
People started doing hot air balloons a long time ago, and at first it was just, can we do it? And I'm sure some people died doing it. And then the military got involved in some of them, and even in World War I, they had to figure out which way the wind's going and look at their maps. That's where we want to drop a bomb. Or they might have just used observation. I just want to say, hey, where are the troops? Where are the troops? And then after the balloon got done, they didn't have if they didn't have a radio and like that, they had to go tell somebody, hey, the troops are right here. And nowadays we have satellites and stuff like that, don't we? So, but they actually did one time. They were even dropping bombs out of those things, which is kind of weird. But the blimps, they did use those. They wanted to use those for wartime at one time. The Germans, their blimps are called Zeppelins. Ever heard of those? And at one time, one chemical that was easy to make with a chemical reaction was called hydrogen. Hydrogen is also less dense than air. And so the first round of them had hydrogen gas in them. There is a problem with hydrogen that is not a problem with helium. Helium is noble gas. It doesn't want to do a chemical reaction. No chance of an explosion or anything like that. Hydrogen is very, very flammable. And so the problem is if something happened wrong, it would blow up, essentially blow up, big time, blow up. So if you watch, if you go home and watch, and if I do have time, I can show, but if you go home and look up Hindenburg. Hindenburg is the most famous Zeppelin that essentially caught on fire and exploded and killed a lot of people. And back then they had, Zeppelins would even park next to a building and you could get out, and they had little places where they could park them in the air. And anyway, I'm not a conspiracy theorist necessarily, except about the last election. Just kidding. But I'm not really a conspiracy person, but I will say we don't really know exactly what caused the fire in Hindenburg. We don't know if it was on purpose or an accident, but somehow that big bag of hydrogen caught on fire, and these people are up in the air, and you can watch it. They have films of it. Some of them are jumping out. They said, well, I might as well try it. I know I'm going to die if I stay here. And it's an ugly film. And from that point on, though, nobody used hydrogen after that ever.
So they use lighter gases to support like that.
Helium was harder to get, and yet it's not flammable. Hydrogen you can actually produce hydrogen pretty quickly with lots of chemical reactions. The United States government actually, because of that, they had this thing called helium reserves. And we still have today. It's interesting. We don't really have any blimps, but the law never changed, and we still have a huge reserve of helium gas. And what happened is, did you notice about a year ago it was hard to find balloons, like helium balloons? Well, the production of helium was way down, and people couldn't find helium gas, and the government had a huge amount of it, but they weren't releasing it because they just thought we need to keep that. That's kind of weird why we still think we need a bunch of helium gas. But who knows? Well, let me talk about the blimp here. Now, the blimp is a little bit more like a submarine. Now, in the ocean, it's in an ocean of air. And so what we're going to do here, we're going to put something in here that is really not very dense, okay? Now, the ship has a weight. The blimp has a weight to it. And we're putting a lot of helium gas in there. And so what we're going to do is, it's possible that the buoyant force, when the buoyant force becomes greater than weight, when buoyant force becomes greater than weight, then the ship starts to rise, okay? And you say, well, that's not much control, and I'll tell you how they control it here in just a minute. But then, let's say you wanted to sink. Let's say you went up there and said, well, it's time to come down, okay? It's just like the opposite of a submarine. Now, so I need to pick up weight. How do I, if I'm a submarine, I'm going to dive, I pick up weight by flooding the ballast tanks. If I'm going to leave, I blow the ballast tanks and put air in it. Now, what I do here is I'm up at the top and I want to dive. I'm going to come back down. How do I do that? How do I pick up weight when I'm up in the air? And everybody know? Okay, so look right here. These are called ballonettes. Those are really big bags, and they're hooked up to motors, so little pumps. And there's one here, and there's one here. These are ballonettes. And so what they do is turn on the pump, and what comes into the bag? Big old fat air. Now, air is a whole lot more dense, about 7 times more dense than helium. And so I'm gonna squeeze that helium into a smaller space and let air come in. Come on in, air. And then what happens? Then the weight of the ship becomes greater than the buoyant force, and we start coming down. Now, if you say, no, I don't really want to come down, I changed my mind. You reverse the fans, you push the air out, and the helium will expand and take up that space, and then buoyant force will become greater than weight. See, it's a lot easier to explain after you've already had the chapter on submarines. What do you think about now? They could actually, if they wanted to go up at an angle, they could actually do that. They could actually fill one ballonette and not the other one. They could do that. They could go down that way. And also, I don't see them here. Here they are. They have these big fans on both sides, and the fans can rotate. They can go in any direction, and they can actually blow themselves and say, I want to go that way. So they can actually take a blimp and go left and right. They can actually even go up and down with the fans like that. Just like a submarine has a motor, an engine, and they actually can go up and down with a motor too. All right, so what do you think? Yes?
Wouldn't they be like really vulnerable because somebody could just shoot it? And then
Oh yeah,
Yes.
and the balloons, of course, the first balloons just had light gas in them, not burners. They weren't hot air balloons. They were just light gas, and they were really quiet, so you never really knew they were there. And maybe with somebody with binoculars, they might be able to see you, and they might be able to shoot you. But they were really pretty quiet. The hot air balloons, they're not very quiet. I don't think they would be very good at spying on people. They're just not that quiet. When you turn on those burners, they're pretty loud. A blimp, that would be pretty good. That'd be pretty quiet. You could have just a little motor moving you. Yeah, I could see that being pretty quiet. That's a good question. All right, and the last thing in this chapter, and then I'll start my demonstrations. This is the last thing in the chapter, and then everything else is going to be demonstrations. Okay. Here's this guy. His name is Bernoulli, and Bernoulli's principle is one of my favorites. It's one of my favorite ones. And when I first learned it, I just thought, wow, I never thought about that. But you're going to see Bernoulli's principle all over the place. If you play any kind of sports, you'll see it. And I'm talking about sports, okay? I was talking to some people yesterday, and we talked about, have you ever been to a stream where the stream was wide and then it got narrow? And if you've ever thrown a leaf or something in there, you notice the leaf coming at you at a certain speed, and then when it gets close to the bridge, what happens to it? It actually, that's a good noise. It starts speeding up. And so what happens is the same amount of volume of water is trying to go through that smaller hole, isn't it? And actually, it speeds up. Now, this little drawing here is a pipe, and this pipe has a big diameter, this pipe has a small diameter, and these are called streamlines. Now, streamlines, if the speed is kind of slow, the streamlines will be kind of far apart. If the speed is faster, the streamlines will be a little closer together. And so these little lines are kind of telling you what's going on in this fluid. And anyway, here, you have a certain amount of speed here, and it should speed up right here, right? So it should go faster here, and it's slower here. Now, what did Bernoulli say? And this is going to bother you a little bit until I teach it to you, right? Bernoulli said, down here, Bernoulli's principle, he says, Bernoulli's principle in its simplest form states that when the speed of a fluid increases, the pressure in the fluid decreases. Now, be careful what I'm saying here. I didn't say that if you squirt water here and make a little nozzle, it'll come out faster. It'll come out faster. But what is the pressure within that tube? It actually goes down. And so when you do this drawing for your homework, notice that the bubbles are big and small, coming out at a certain speed, and then you make them go into this zone here of faster. And why do the bubbles get bigger? Because the pressure inside that tube actually decreases and the bubbles start to expand. I always like to ask this question. If I had a pressure gauge here, and let's say, I just made up a number, can't see it. Let's say the pressure is 5 units of pressure. What would the pressure be here in this tube? Lower. It'd have to be maybe something like 3. You get that? And so that's interesting. And you say, well, does that really cause some weird thing that I'm going to see in my life? Oh, yes. Oh, yes. You're going to see a lot of this. All right. I'm going to show you one big area, okay? Bernoulli's principle. Here we have a wing. This is a wing cross section. And what they do is, the way you want to make the wing is, you want to make this down here, this part of the wing is going to be a shorter, this is going to be a longer path, this is going to be a shorter path, and the wing's going to have a little bit of a scoop here. I didn't show much of a scoop here, but, and so this is going to tend to cause a little bit slower air here and faster air here. So the wing is made so that air will move faster over the top than over the bottom of it. So what does that mean? Faster air means lower pressure. I want you to think about this. This is higher pressure, lower pressure. If there's one big idea in this chapter, just same thing in weather. High pressure systems nothing sucks, but there's a lot of pushing going on. High pressure tries to fill in low. And the air just says, you know what? I'm going to fill in that low pressure. Well, the wing's going to get in the way. That's right. We want the wing to get in the way, and guess what happens? It makes the wing go up. And if you know anything about flying, you know there are 4 major forces about planes. One of them is your plane has weight. That's bad. That makes the plane crash, okay? And what does the wing shape do if it's going? It produces lift. That's good. Lift, weight. The motor tends to produce what they call thrust, which makes the plane go that way. But when you run into all this air, it tends to produce what? What's that called? It's called drag, okay? Drag is friction, isn't it? Anyway, those 4 forces are kind of how an airplane works, all right? So anyway, Bernoulli's principle has to do with the shape of the wing, creating low pressure up here, faster moving air, slower moving here. I was talking to some people yesterday, and I remember the first time I heard it, I couldn't believe it. I remember being in a windy condition, and I had an umbrella. And I remember the umbrella was actually pointing, the wind was coming this way, and I actually was pointing the umbrella that way, almost like that. And then the umbrella inverted anyway. But before I knew this, I thought for sure that the wind must have got underneath the umbrella and turned it upside down, inside out. But it didn't. When it hit that round umbrella, it started moving faster, and that created a low pressure zone here, and my air underneath the umbrella was high, and it was my own air underneath my own umbrella that was actually popping the thing inside out. I've seen high winds go across buildings. You've seen them rip the roof off, right? I know what you're thinking. You're thinking, well, some of that wind must have gotten inside the building. Somebody left the windows open or something, and the wind must have gotten into the building and blew the top off. I don't think so. I think the wind went over the top of that building, increased its speed, and created a what? A low pressure system. What happened to the air that was in the building? Just mind its own business. It said, I got to fill in that vacuum, and it blows the roof off from inside out, doesn't it? This one, if you're a sports person, okay, this is a hard picture. Anybody baseball players in here? Okay. What you have to think about is this is a top view. I know you're looking, you're saying, that must be the ball going, no, you're on top. You're in a drone looking down, okay? What if I were to throw a baseball with a spin? Okay, now I'm going to draw the baseball, and it's going to spin and move this way. Everybody get that? It's a curveball. Watch what's going to happen here. So the ball's going like this. It got little seams on it, doesn't it? That's important, those little seams. And what's going to happen is, I want you to think about this. The ball's going this way, isn't that right? And is it any different if the ball stood still and the wind went that way? Is that any different than the air sitting still and the ball going that way? Don't you still? It's kind of like a wind, isn't it? So watch this right here. When that ball, this is a top view, when it curves like this air that's trapped around the ball, it's going to encounter this air and slow down. It's going to slow down. Now, what's going to happen to the air over here on this side of the ball? It wants to go this way. Well, I'm going that way anyway. So it's going to speed up. Okay, I'm looking at your faces. Sorry. Okay, now, one more time. This is a top view. And so this part of the ball is slow air, and that's higher air pressure, and there's low here. And what does this air want to do? It wants to fill in the low. So as the ball, here's a top view, as the ball is coming toward home plate, the air keeps going, you got to go that way. And it goes, and see? And it makes the ball curve. And of course, people can throw sliders. They can throw it the other way. Instead of making the ball go like this, instead of going like this, they can go like this. Some pitchers are really good, and they can make the ball go like this. And if they're really good at it, the batter sees the ball coming, all of a sudden, zoom, and then it starts dropping. If you play tennis, the hairs on that ball are trapping a lot of air. And anybody who plays tennis knows that you can, what if you make the ball spin like this? What happens to it? You can hit really hard, but what will go out? If you're not good at it, that's me. But if you're really good at tennis and you put top spin on the ball, you hit it really hard, and what happens? It still stays in the court, doesn't it? Or you can go like this. Can you take the ball and slice it? And you can make the ball go like this. All right. How about golf ball? Golf ball, little dimples. What's that all about? Ooh. Have you ever seen a golfer do that? Can a golfer make a golf ball? All right. Sometimes, if you're really good, you do it on purpose. If you're bad, you didn't, for example, I'm not that good. I only play golf about once every 2 years. But if I hit that ball hard with a driver, and I don't hit it right, my hands aren't in the right place, that ball will just go, woo, and it'll slice. It'll slice way off course. But some courses are made to have a dog leg. A dog leg is a golf hole that's not straight. They might have some big trees here, and on purpose they made a dog leg where you have to go here, then you have to go here. But what if you had a really good slice? You could go around the trees. Anyway, so that's what. How about in soccer? What do you call it when you bend the ball? Any soccer players in here? Darn. Soccer? Are you not bending the ball? What do you call it? You call it something else. Could you, from a corner kick, if the goalie was asleep, could you kick the ball in from a corner kick?
Yes.
Not little kids, but any good soccer player can take the laces.
Good morning, students. Pardon the interruption. We have a couple of important lunch announcements, so rhetoric students and teachers, please listen carefully. Because of the 2-hour delay today, we have an extremely short lunch period, so we will be leaving for lunch at 11:40, and we are done with lunch at 12:10 as usual. So seniors, that means that if you are going out for lunch today, we want you to go close and drive very carefully. It's a mess out there. Sophomores, we're going to ask you to please eat upstairs in Caldwell Hall today by the senior lounge so that we have plenty of room for everybody. And also, if you are in Miss Gilbert's 11th grade pre-calculus class and you would like to come in the last 10 minutes of lunch to start your test, that will give you a full hour for the test. Again, Miss Gilbert's 11th grade pre-calc, you have the option of coming
Well,
in from
that's just
lunch
giving you more time.
and 10 minutes early to start your test so that
Okay.
you'll have the full hour. One more thing, that our lunch will be very short today, so we need you guys to get into the lunchroom, eat your lunch very quickly, and then we'll be leaving the lunchroom at 11:55 today. Have a great day. Thanks.
All right. All right, real quickly, darn it. All right, now, you actually, if you kick it right, you kick it with your laces, okay? And if you kick it right, the ball will spin, okay? And it'll curve and actually could go into the goal. Again, a goalkeeper would have to be asleep not to see that. But on the other hand, if you curve it a lot, it might go behind the goalkeeper and maybe some other person can head it in or something like that. And so you're going to see spins in a lot of sports, and those are all Bernoulli's effect. All right, now I'm actually finished with everything in the chapter, and now it's just a matter of you study a little bit. So I'd like you to study a little bit tonight, and then I'm going to, I thought I'd have some time. I guess I could do a couple, demonstrations. I have all of my big ones are tomorrow, okay? All of my big demonstrations tomorrow. Let's do a couple little ones.
That's the woman.
Okay, now, this right here is a cheap version of Magdeburg Hemispheres. This is a little more expensive, but not that expensive. And these little, you call them suction cups, but they don't really suck. I don't know of anything that sucks. But I do know that if I were to push the air out underneath these, that there'd be quite a bit of air sitting on top of them. And so it's very possible that I could do that. But I can also do this.
You're not supposed to do that.
No, you can. If I were to put this area a little bit of water there, right now
Oh, that'd be hard.
all I have to do is if he deforms it a little bit, if he just deforms the shape a little bit, air will get in, okay? Yeah, see that? I'm not gonna spit on it. But if I put a little bit of water in there, he might have a little more trouble.
Because wouldn't that seal off all the?
All right, now, again, I'm sorry. I will do an entire period of demonstrations tomorrow, and I think you'll like them. Very memorable. This is one real quick. You take a little piece of paper like this, and you put it underneath the lid. What I'm going to do is blow really hard, and what you do is in 10 seconds, see how many times when I blow really hard, it's going to make it hit my chest over and over and over. See how many times it hits my chest. Ready?
What?
Because I was lying to you, because when I blow air out of here, it goes really fast. If it goes fast, that's low pressure. And what's all this other air going to get in here? Look at this air right here. It's going to say, I got to fill that in. It produces lift. Okay, so you can do that one home. That's pretty easy. All right, I'm out of time. All right, I will try to make sure you're here tomorrow, because I'll save all the demonstrations for tomorrow.
I was